Okay, and we're recording. So last time we were talking about surface integrals. A couple of different kinds of surface integrals. We started off with scalar surface integrals. Quantity per unit size times size gives you quantity. I mean, it's a very chop it up, add it up kind of a deal. Where things get a little weirder is when we start answering a different kind of a question, and flux is the physical problem that leads us to it. Specifically, now recall from chapter 3 that flux allows you to compute how much fluid is passing through a surface, right? And so it's a nice thing. It's very physically a natural thing if you have a fluid flowing, but it's very reasonable to want to know how much that fluid is flowing through a given surface and per unit time. So we, as usual, in a calculus class, did they're ringing the bell early. Weird. We chop it up, add it up, right? So we take the entire surface, chop it up instead into a bunch of little pieces, like so, and then on each little piece, notice it's approximately flat. Notice that as small as it is, the x points being as close as they are, the vector field's approximately constant. And we went through all this last time, so that's why I'm going quickly here. The big idea, though, is that motivates this construction for computing that flux, and we notice that this is a qualitatively different kind of an integral than a scalar surface integral. So in particular, looking at this notation for it, notice that our integrand, not a scalar, it's a vector field, right? And notice further our differential, describing for each summand, what do we know about, what is, relevant about the piece of surface, also a vector, not a scalar. And so these are called vector surface integrals, which I like to streamline. Just to save a couple of syllables, I call them flux integrals because, well, after all, they compute flux. Okay. All right. So this is about where we left off last time. Oh, no, I guess we did talk through some of this business. Reminder, setup we already know. Right? We already know that if you have a parameterization of a surface, giving position as a function of S and T, let's just say, we already know that output area relates to input area by way of a stretching factor, right? And we already know that stretching factor is computed by this formula. It's the same. That's exactly the stretching factor that we used in doing scalar surface integrals. So fitting that in, though, let's see here, just to clean up. Fitting that in with our flux integrals. Notice what I'm going to do is just plug in ds is magnitude of capital N times ds dt. Just plugging straight in. And then realizing that this product here is a vector that is perpendicular to the surface, just like capital N is. Its magnitude is the magnitude of capital N, just like capital N's magnitude is. We argue, I choose my words carefully there, surely this then would be capital N. It looks like a duck and quacks like a duck. Same direction, same magnitude, isn't it? I mean, it seems like it is. Seems like we should rewrite that as capital N. Again, I want to make it clear, I am committing a math crime there. What I write is not true. And I'm going to reveal what the problem is in just a minute. But we've got enough going on as it is without worrying about the little technicality problem there. And what I want to do first is take advantage of the fact that we now have a formula that will compute flux for us directly out of a parameterization. Right? You parameterize your surface. This is plug and chug. All right, so let's see an example of that. We'll come back to the mistake in a minute. Here's a vector field. Here is a surface. Let's compute the flux of that vector field through that surface. Step one, we want to use this formula that allows for pulling back through a parameterization, we're going to need a parameterization. So when you're going to use this formula, step one is always to parameterize your surface. This surface being a graph, I'm going to use the graph parameterization. I haven't been counting. How many gongs have we got from the... It seems like is it 75 o'clock right now? That's weird. Whatever. Anyway. Okay, so we've got our parameterization here, and now we just follow the formula here. And again, we're going to have to take partial derivatives of that parameterization. You're going to have to cross them, and then we're going to have to take the wait a second. Are we going to take the magnitude? No, we're not. We're not going to take the magnitude because we don't need the magnitude explicitly. In fact, we're going to just use the capital N vector itself. This is one of the sort of unexpected conveniences of doing a seemingly more complicated thing. A vector surface integral sounds harder than a scalar surface integral. But the upshot is you don't have to compute the magnitude of capital N, you just need capital N itself. The magnitude's wrapped up inside of it, and that's fine. It's there. I just don't need to explicitly compute it. It's already inside of this. Okay. So here we go. Parameterization. Partial derivatives. Cross product. And we're in business. That is my capital N from the handy-dandy formula that I'm using here. The vector field, now there is a little bit of an annoyance here. I mean, the vector field, right? I mean, the vector field is this. But keep in mind, I have to evaluate the vector field at my parameterized point. Right? So the vector, sure, it's z squared, x squared, y squared, but don't forget x is s. Right? So when you rewrite the vector field in terms of the parameterization, x turns into s. Likewise, y is t. Right? And z is s squared plus t squared. Excuse me. It is really easy, by the way, to accidentally oops and forget a square. So notice z is squared, but z is itself the square, sum of squares of other things. It'd be really easy to actually forget this square right here. Right, so it is just plugging in, but it's plugging in that you have to be careful about. So, warning. All right, how are we doing so far? Everybody happy? Yes, question. Yep.
Could you explain why the capital N vector's direction is the same as the orientation unit vector?
Yeah, well, so I'm gonna have to be sloppy here on purpose because I've deliberately avoided the truth of the matter. Right, I am committing a little math crime that I am going to fix in a second. For the moment, my argument was that capital N we know is perpendicular to the surface.
Yes.
And little n here, the orientation unit normal, perpendicular to the surface. And the idea is that, if you have a plane, then perpendicular, there's really only one direction that's perpendicular to the surface, or so it would seem. And again, I'm committing a math crime on purpose. I'm going to come back and fix it in a minute. But that's the case that I made here to lead me to this formula. And I will fix it on the next page. Yeah. Okay. Good. I'm glad you're concerned about that because it is wrong. Yeah. Okay. But it's not super wrong, and we're going to fix it in a jiff. Okay, so all together then, we have turned flux, namely by way of this parameterization formula, into this plain old, regular old double integral. And notice this is just a double integral. You can dot it out and get the integrand and Chapter 5 techniques and compute it up. Okay. All right. So, yeah, what was my crime? What was the oops? And it has to do with the choice of parameterization. And it turns out that how you parameterize does matter a little bit. Here's a picture of what's going on. Now keep in mind when you're given a surface, and if the question asks to compute the flux through the surface, it has to be made clear which direction is the asker, right, the question asker, viewing as being the positive direction through that surface. You have to have an indication of such to know how to keep track of what's plus and what's minus. So, for example, it could be that we're interested in viewing flux upward through the surface as being positive. And that we, on the other hand, we could instead be wanting to view downward through the surface as being positive. I mean, just as a silly example, if you're playing basketball, right, you have a surface which is defined by the hoop, right, the surface in between there. It's very important that the ball go that way through that surface. This way is not okay. Right? So that's what we're talking about here. Which way is you might say, the right way through the surface. So it could be either of these directions. These are, again, reminder of what we call the orientation of the surface, and it has to be given in the statement of the question explicitly or implicitly, one or the other. Okay, here's the thing. When you do a parameterization, the parameterization itself tells you what its partials are going to be, which tells you what the cross product is going to be, which then tells you effectively what your parametrized unit normal will be. That comes directly out of the parameterization. So let's take stock here. The question comes with one or the other of these being defined to be correct. Being defined as, this is what positive means, whichever one of these it is. And then we pull a parameterization out of thin air arbitrarily with no consideration given to what the orientation is for the surface. We just write down a parameterization, which means we arbitrarily, out of thin air, kind of randomly pick effectively what orientation we're going to use with our parameterization. And it's a coin flip. Maybe it's right, maybe it's wrong. Right? The surface could have been oriented in either of these directions, and our parameterization was completely blind to that when we wrote it down and therefore got our parameterized unit normal. So that's the problem. When I said on the previous page, and I said, hey, looks like a duck, quacks like a duck, right? Here I have a product. This product vector has a direction that's perpendicular to the surface. Well, sure it is. It is perpendicular to the surface. And that is not just one possible direction. There's two possible directions that this could point. Right? And when I then just assert that this product is equal to the normal vector, keep in mind the normal vector, I'm going to have to scooch out here, the normal vector points in the direction of the parameterized unit normal, which is not necessarily the same as the orientation unit normal. So this was the problem. This was and again I put an asterisk in here, right? I was confessing that I was sweeping a subtlety under the rug here. The subtlety under the rug is I was assuming that these orientations are the same, and 50-50, coin flip. Maybe it is, maybe it isn't. That's the problem. So now, how we fix that is the next topic, but before we go on to that, does everybody see what the problem is? Okay, all right. Now it's tempting to say, well, just, when you write down your orientation, just make sure to orient correctly. And the problem there is, when you write down let me go back up to here. When you write down a parameterization, at a glance, without looking over here to what comes next, just at a glance, just looking at this formula for the parameterization, in what way is it clear whether this is up or down? Right? How can I tell at a glance which way this orients the surface? You can't. At least not in general. So that's a little bit of an issue. You can't just rely on, I hereby declare I will always parameterize correctly. You just can't know it. Right? So here's the good news. You don't need to actually worry about, as you're parameterizing, whether you got it right or not. Because if it turns out that you parameterized upside down, again, it's a coin flip. You'll see later. If you got it upside down, it's easily fixed. You're just off by a minus sign in all of the terms of the summation. You just fix by throwing in an extra minus sign. And that's all there is to it. Let me show you an example. Oh, before the example, real quick. Assuming you get the orientation correct, nothing else matters. Your value that you're going to get for this integral, it's going to give you the same value no matter what, as long as you have the orientation correct. Was that a hand? Yeah.
Is there a way to ensure that you always have the correct?
Sadly, no. Not reliably. Not in all possible cases. I mean, there's a couple of little. One trick occurs to me, but it's really not worth it. It's better to just do what I'm about to show you, which is ignore orientation until you have your capital N vector, and then fix it if necessary. Let's see an example here. Okay, now this question here, this example, practically identical to the first example that we looked at. Same vector field, same surface. The only difference is that this one is oriented downward, whereas initially, in this first version of this example, notice it was oriented upward. Okay, so practically the same example. Let's go through this new version, see what happens. Notice step 1, I parameterize. No consideration of orientation. Don't worry about it. We'll deal with that later. Just parameterize whatever way is going to be the most convenient for you. And then take your partials, take a cross product. Now you know your capital N vector. Here's where you have to pause and take stock and ask yourself, wait a minute, okay, did I orient this thing the right way or the wrong way? And here's the thing. The surface was given to be oriented downward. Let's look at our capital N vector. Is this capital N vector oriented what you might call downward, or is it oriented what you might call upward? And there's a few things to say about the language, but if you notice this third component being positive, that means that this capital N vector, it's kind of like this. I mean, it's not exactly straight up. Of course, it's not exactly straight up. The surface isn't flat, as would be required for the normal to always be exactly straight up. So we have a curved surface that's oriented kind of somewhat upward, but it's in no sense downward. So by seeing this discrepancy, seeing that and this are in conflict, right? I realize I did not parameterize this consistent with the given orientation. And so that means that if I proceed with this calculation, I'm going to get a wrong answer by a minus sign, and I'm going to fix it by just literally sticking in a minus sign in the middle of the computation. Did I see another hand somewhere? No? Okay. So again, don't make the mistake of thinking, I've got to parameterize it right. If it's not parameterized right, then it's, oh my gosh, it's all messed up, and I'm going to be, I'm going to get nonsense as my answer. No, parameterize any way you want. Just check after the fact to see if you oriented correctly or not, and then if you oriented wrong, throw in a minus sign. And don't, for crying out loud, don't re-parameterize in the hopes of getting a correct parameterization. What do you think? Does that make sense to everybody? Okay, now a couple of little details I got to talk through here. You do have to be careful where you pop in the minus sign. That does matter. You can't just, I parameterize backwards, and so I'm just going to put minus signs kind of all over the place. That's no fair. Let me explain why. You've been asked to compute a flux. That's the thing you were asked to compute. You have not been asked to compute negative flux, right? So you have to compute what they've actually asked you to compute. And flux is computed with this formula. The vector field, right? The ds is a vector pointing in the direction of the correct, by definition, ds points in the direction of the correct unit normal, the orientation unit normal vector. So this is always correct. Where things get off, or where things might get off, and in this case did get off, is where we rewrite in terms of capital N. This is where your parameterization shows up, right? All of the initial parts of this were given. This is all in terms of the defined orientation. It's when capital N shows up that your parameterization normal shows up. And if you have an inconsistency, then this is where the minus sign belongs. The correct orientation is the negative of what I'm going to compute because I parameterized upside down. Does that make sense to everybody? So that's where the minus sign goes, not up here. If you put it up here, it's wrong. And again, just why do we care about this? Some students would take the point of view of, well, I mean, if I put a minus sign there and there and there, I still get the same answer. So who cares? The reason we care is there's some false statements in play here. This suggests that the flux is the negative of what it's defined as. That is not true. That is a false statement. I mean, it's just not true. Importantly, not true. And it also suggests that these things here are equal. Again, not true, right? If you have minus signs on both sides of the equation, like we do here, that suggests these integrals are equal, but importantly, that is kind of the whole point. This one is the negative of that one. So, it's wrong to put that minus sign there. You have to put it here. Okay, so I hope that makes sense to everybody. So let's move it along. Notice, of course, now we missed the minus. There we go. This is again just a double integral, and you can, plug and chug. Chapter 5 techniques, compute that double integral. Okay, how are we doing? We just talked about a lot of stuff there. Everybody's happy? Okay, so let's talk about language a little bit. This is unfortunate. The language describing orientations. I mean, if you want to get really nitty gritty about it, an orientation is an entire set of vectors, an entire collection of unit normal vectors defining, again, which way is what we call the positive direction through the surface. There is not a single word that is going to precisely describe all of these vectors all at once. That's not realistic. I suppose I could write down a formula for these, but when you're stating a question, you don't really want to get bogged down in, not even being able to ask the question until you've already worked out half of the solution. Right? So we don't want to do that either. So the idea, the way we choose language to describe orientations is not to be precise. It's to unambiguously distinguish between the only two options that exist. And so let's look at our two options here. Our second option would be sort of the like this. Right? These are our two options. We've got the orange orientation and we've got the green orientation. That's it. Those are the only two possibilities. Rather than describe them perfectly, let me just point out that all of those orange vectors, they're all at least somewhat up-ish. Right? They all have positive z components, and so I'm going to loosely, sloppily call that upward. They're not exactly upward. No, of course not. But they're all somewhat up-ish. And notice that these green vectors, none of them are in any sense up or even up-ish. Right? So when I say upward, that unambiguously indicates the orange orientation and it excludes the green orientation. And so it's perfectly clear what we mean by upward, even though, again, upward is not a perfect description, but it is entirely unambiguous. And then likewise, downward. All of these green vectors are at least somewhat downward-ish. And none of the orange vectors are in any sense downward-ish. And so downward, again, not exact, it's not precise, but it's completely unambiguous. All right. So this is a great choice of language to distinguish between these two orientations. And that's the way people are going to describe orientations in talking about which way they want you to consider positive through a surface. Okay, now here's another language option that I kind of see a point of view on. Inward versus outward. You could make the case that the orange vectors all kind of point, in some sense inward. They point to where the cereal is, right? And the green points to where we hope the cereal isn't. Right? So, inward versus outward, I kind of get it. The reason I put a on that is that technically this surface as drawn is not a closed surface. There is no inside and outside, technically. So, look, the speaker will understand what you mean. So, I guess it's okay, but notice it's really much better to say, in this case, upward versus downward. It doesn't rely on the speaker kind of catching your drift. This is entirely unambiguous. Does that make sense to everybody? Okay. All right. So with that in mind, there's a couple other cases to think about. If you're looking at a sphere, right, you can't say upward versus downward. It just doesn't work at all. Let's see here. This orientation here, some of the vectors are upward. And some of the vectors are not upward. So is upward a fair description of that green orientation? Not really. And even worse, the orange orientation, some of its vectors are upward. So upward is really ambiguous. It doesn't distinguish really at all between the two possible orientations. So this is terrible terminology if your surface is a sphere. It's great if you're talking about a cereal bowl. Terrible for a sphere. Okay, etc. So always make sure to tailor your language again, don't try to be precise about what the orientation vectors are. Try to be unambiguous in the choice between the two options. And that's how you should use the language, and that's how you should interpret the language when you see examples. Just real quick, one last option for something like this. For something like this, upward and downward doesn't work. Inward and outward, again, kind of, sort of, not really super happy with it. But notice whether the vectors are pointing somewhat in the positive y direction or somewhat in the negative y direction. Again, not perfect, but it is 100% unambiguous. So that'd be the best way to do it for this surface. What do you think? Is everybody on board? Okay. All right. Alrighty. Okay, so so just to take stock, let's see here. We wrote down this formula for flux, kind of sloppy treatment, deliberately sloppy treatment, but ultimately this is, other than orientations, this is the right answer for how to do a parametrized integral to compute flux. And the only additional point is you have to think about whether your parametrized orientation is right or wrong, depending on what the given surface orientation was. You just have to look and see, and if it's right, yay, and if it's not right, toss in a minus sign. Okay. All right. And off we go. Next thing. You get lucky sometimes. Y'all have heard me talk about good fortune, right, previously. Symmetry is one of my big favorites. Double integrals and triple integrals, gotta love symmetry. Huge fraction of the integrals I saw as an undergrad, snap, boom, symmetry argument. Right? One of the most powerful computational tools for integration that I'm aware of. So really awesome. And now the lucky kind of coincidences I'm going to show you here, maybe not quite as common and powerful, but when they work, they're equally awesome, equally useful. In those cases, they just maybe don't come up quite as much. So here you go. First example. Suppose we are looking at this sphere, right? And oriented outward, by the way. And I want to look at this vector field and compute the flux of that vector field through that sphere. Fine. Now, you could take your formula for your sphere, realize that this is a spherical graph, right? Rho equals. So this is a spherical graph. You could write down the spherical graph parameterization. It's going to have a bunch of trig in it. And you could take a deep breath and plug and chug. And if you do, I mean, it will work out. And it also will be bulky. And, all else being equal, a lot more trouble than what I'm about to show you. So what I'm about to show you is to take advantage of the symmetry and keep in mind that when you're talking about a sphere centered at the origin, which this is, we've made this observation in a different context previously, but the normal vector, and this is just spheres. This is the way spheres work. The normal vector is always parallel to a radius vector. And in this case, the position vector is a radius, again, because the center is at the origin. So, again, the geometry of spheres, and this is a unique, spheres are, uniquely holding of this feature. Normal vector is a multiple of the position vector. Right? And so you get an easy formula then for your normal vector. Your normal vector is just that. I can just boom write that. I don't even have to parameterize or anything. Now, I haven't done a pullback. This is not a regular double integral. I can't use chapter 5 techniques on this integral here. But I was able to at least kind of write something down, and that gives me a foot in the door to take my vector field. And let's just, kind of multiply this out, and who knows, maybe you get lucky. Wouldn't that be nice? And before I get into the parametrizing and that whole tedious thing, and check it out, this dot product 0, game over. Right? That's kind of awesome. So, that's a pretty cool deal. Now, how often is this going to come up? Well, sometimes. I hesitate to say it comes up as often as odd symmetry results come up. But spheres come up a lot. Right? In physics is chock full of spheres. Engineering, a lot of y'all are engineers. Chock full of spheres. Right? So that part of it, and this little move right here, comes up a fair amount. So at least that much of it is fairly common. And whether the dot product will turn out to be 0, like it did here, will this, how often does that happen? No comment. But certainly some, and certainly this is very much worth my time when I was an undergrad, and I think it'll be worth your time as well. Okay. What do you think? Questions? Is everybody happy with this example? All right, next example. We got a surface described, kind of a weird way, and I want to talk about flux through that surface of this vector field, which is kind of scary looking. And yikes, right? That looks like it could be a tedious calculation. So let's see if we can avoid that. And what I'm going to do is point out that a neat thing about the way this surface is described is that it's part of this plane. It is entirely a subset then of that plane. And there's some pretty sweet stuff that I know about this plane. Now the rest of the details, excuse me, the fact that the actual surface itself is a subset of that, exactly specifically what points are in that subset, it's going to end up not mattering, believe it or not. It's just that part's going to kind of go away. But the fact that it's all sitting inside of this plane is where the big payoffs are going to be. And there's two parts of this payoff. One is, this is a plane. It's an easy plane. It is a plane that is perpendicular to the y-axis. And so the normal vector is parallel to the y-axis. And so, boom, we know our normal vector, our orientation normal vector is just 0, 1, 0. Now, how do I know it's not 0, negative 1, 0? Because it says it's in the positive y direction. Right? So, I instantly know what the normal vector is. That allows me to write down this right there. And that simplifies things quite a bit. In some sense, two-thirds of the terms in the dot product I just instantly made go away because they're being multiplied by 0. Everybody see what happened? It's already pretty cool. Well, here's the other thing, though, that's nice about being in that plane. Because my surface that I'm interested in is entirely within this plane, that means that for all the points I actually care about, for all these light green points in this actual surface S, they all have the feature that y is equal to 3. And if you notice, plugging in y equals 3, that makes this second component of the vector field 0. Well, so let's toss that in here, then. That second component of the vector field, 0. Just because of the fact that y is specifically 3. So, alright, so what was I asked to compute? I was asked to compute flux. Flux requires dealing with F dot n, and if you just write it as F dot n, well, F is a big ugly formula, and n, oh gosh, we have a technique. We got to parameterize, and then take the partials, take the cross product, divide by the magnitude. We have this whole spiel, right, for finding what little n is. But just by reasoning from the context, I see that certain coordinates of those vectors I immediately know to be 0, and in fact, as it turns out here, that means all the terms in the dot product are 0, and that means, again, game over. No real work. I didn't have to parameterize and crank anything out. I just observed that, key facts, and we're done. What do you think? Everybody follow that one? There we go. Everybody feeling good about it? That's another thing to keep your eyes out for. Very useful sometimes. All right. So, y'all remember when we were doing vector line integrals, we were able to rewrite in terms of coordinates. And we got this weird notation that I called coordinate line integrals. And basically it's a sort of a notational alternative for vector line integrals, and it's bulky and it's counterintuitive, or at least non-intuitive, and not clear why we'd want to use it, but there are certain advantages. Anyway, so notational alternative coordinate line integrals. Same story, just now with surface integrals. Okay, so here's the deal. We've previously noticed that n is that product, which we can write out in coordinates, which I can multiply out the cross product, and as it turns out, and y'all can just check this for yourselves, but all of the coordinates of the cross product, what are the odds? They all end up being Jacobian determinants, little 2x2 Jacobian determinants. A little unexpected. Nevertheless, it works. So I made that observation last time, I think it was, or maybe the time before, and I just said, it's going to come up and be useful a little bit later. Here we are. Keep in mind what we're interested in is now the ds vector. The ds vector kicks in this extra factor of ds dt. And multiplying by ds dt, distributing that ds dt to each of the coordinates. Now, let's look at each one of these. Let's look at this thing right here. Let me get rid of all this. Let's look at this thing right here where I've got partial yz partial st times ds dt. Well, that really looks exactly like we wrote stuff like this down when we were doing change of variables, and this is where we would, again, full apologies to propriety, but we'd pretend like those kind of cancel, kind of, sort of, which they don't. Right? But, because this is not a fraction, this is a determinant, so it doesn't. But this, again, you can kind of get away with we've already established that this behaves as if this cancellation is legal. So as we have done in the past, it feels like we should be able to just call this dy dz. That's exactly what we did when we were doing change of variables. And then likewise, this, in the past, we would have just called dz dx. And likewise, this we would have called dx dy. Now, geometrically, what does this mean? Does this make any actual geometric sense, or is this all purely notational nonsense? It turns out, actually, there's a really good geometric interpretation of this. Is actually extremely natural geometrically. I just don't have time in Math 219 to talk about it, and it's sad because it's a beautiful collection of little ideas. It's not even all that hard. It's a 15-minute conversation. And we just don't have time in this course as it is, so you don't need to understand the geometric interpretation of this. But if you're curious, please come to office hours. I would enjoy talking about it. It's a nice little discussion, and I'd be very happy to show you in office hours. So just come on by if you're curious. But as far as Math 219 and what your responsibilities are on this, you just need to know that we rewrite it like this. You don't need to know why we rewrite it like that. Okay, so punchline then. ds. We've got a coordinate notation for ds, which I just stick right into our formula for flux integrals. And don't forget our vector fields got coordinates. Let's say again that they're PQR. And then just analogous to what we did when we were doing coordinate line integrals, you dot this out and you get that. And lo and behold, then we have a new sort of notation, a notational alternative for flux can instead be written like that. And these are coordinate surface integrals. And in the context of Math 219, which one do we like better? I have pretty strong preference myself. I like this one better. It's more compact, right? A lot less pencil lead, a lot fewer, pixels, pen strokes. I geometrically understand this, right? The ds vector has a natural geometric meaning. This is interpretable. F, that's the vector field I was given. This means something. It's like fluid flows or whatever, right? So this is natural, it's compact, it's understandable. This notation is bulky and it's not clear from what I've told you what this actually means, and geometrically how do we make sense out of it. So this is, for the context of Math 219, not really as useful for us, right? So why then am I wasting your time with it? And there's two reasons for this. One is what I like to call a cultural point. If you want to know what differential forms look like, and you've heard me say differential forms previously, it's a sophisticated and powerful point of view on vector calculus that you can, if you want to get a glimpse of it, just take a look at Chapter 8. But it's a very powerful, very sophisticated point of view, and frankly, if you want to do flux with differential forms, it looks a lot like this. Not exactly, but it looks a lot like that. So this is basically differential form notation. And so, as such, from a cultural point of view, it's good to know that, hey, this is not a bad idea. This is an awesome idea. It's just hard to see why. Right? And those advantages are things that we're not going to capitalize on in this course. The other reason that I feel it necessary to show you this notation is that other people like it, other people will use it, and therefore you're going to see it, whether you like it or not. Right? So it's out there, and I need you all to know that when you see something like this, So surface integral, by virtue of the fact that the domain is clearly a surface, but the differentials are not surface area. They're not the ds vector. They're coordinate differentials on a surface integral. Very weird. It jumps right out at you when you look at it, right? When you see something like this, you should be thinking to yourself, oh, yeah, that's flux. It's a flux of, well, whatever the vector field is, right? I mean, whatever these integrands are, that makes up the vector field that's your actual integrand for your actual flux integral. So heads up, when in future engineering classes or what have you, you see, and I think you will, this, translate it into these terms for the more relatable point of view. Okay. Pausing. Questions? All right. Again, if you want to know what this means geometrically, come to my office. I'll be happy to show you. About 15-minute discussion. Okay. Last thing we're going to have time for is it's kind of another cultural point, and that is that it's good to know that line integrals and surface integrals are both examples of integrals of differential forms. Now, we're not going to explicitly use that, and again, you're not responsible for any actual differential forms in this class. But culturally, I think it's a good idea to realize that they are, and when people talk about differential forms here or there, you can know, okay, well, that's some fancy version of line integrals and surface integrals that you do understand. But furthermore, knowing that these two things connect to the same thing basically implies that they should also kind of relate to each other. And that's what I'm going to show y'all. And it happens massively. There are tremendous analogies between line integrals, vector line integrals, and vector surface integrals. And this is what I want to point out with these diagrams and equations down here. So you'll notice on each side of the, well, let me do this in neutral color. There we go. On each side of the line there, I have a parameterization. Here I have a parameterization of a curve, and all the usual players, the usual participants in the conversation, the story of a parameterization of a curve. And then over here, parameterization of a surface, and again, the usual players labeled. So let me just point out how much these pictures have in common. Here we go. First of all, there's a parameterization in each case, fine. Next, the derivative of a parametric curve is velocity. The derivative of a parametric surface, well, let's think about that for a second. I mean, there's actually a couple of partial derivatives, and capital N is neither of the partial derivatives, but it comes directly from those partial derivatives. It's a cross product of the partials. So I'm going to say N, it's a stretch to say that it is a derivative, but it comes directly from derivatives. Think of it as playing a role kind of like a derivative in this surface integral context. So I'm coloring N and V with light blue to point out that they have this analogous sort of origin and role from derivatives. Next, let's see here, I'll use orange. The unit vector in the direction of the velocity gives me the tangent vector, which defines the orientation. The unit vector in the direction of capital N gives you the unit normal, which defines the orientation. So both of these derivatives, point in the directions that define the orientations. So there's that. Pointing in the same direction, we have these vectors dx and ds. Both of these vectors, again, play analogous roles. They both point in the direction of the orientation, and they both have magnitudes equal to the size of the piece that they're describing. the length of this little piece of curve, the area of this little piece of surface. Right? So, all right, fine. Where it starts to get really interesting, though, is when you start making the connections with the various formulas relating these quantities. So notice, for example, the dx vector, the ds vector. Let's see here. We have the velocity and the capital N. We have then the unit tangent vector, the unit normal vector. We have the length differential, the area differential. Oh, I could talk about the pullback differential dt, and then over here the pullback differential ds dt. And look how in these equations, now all these equations here are old. We've seen all those equations before. But analogous objects play analogous roles in the equations too. That's weird. Right? This is very unexpected. If you just looked at it, if someone were to tell you, hey, we're going to do a certain calculation about computing work, and then we're going to do a higher dimensional calculation involving this totally different physical quantity called flux, define a totally different quantity called a surface integral. If someone were to tell you, yeah, I'll bet you those calculations are going to look a lot alike, there'd be no reason to believe that they're right. And yet, look how much they have in common. That the analogies are stunning. And it's not a coincidence. The reason that these calculations look so much alike is because they're the same calculation. Both of these are integrals of differential forms. Line integrals, surface integrals are both morally the same thing, differential forms. And so it's really, from that point of view, no surprise that they're structurally identical. I'm out of time. See y'all later. Y'all have a good day. Just for the record, we are done now with the rest of this is just more examples of analogy. So we're done with section 7.2. We'll pick up with 7.3 on Friday. Okay.